Hi, AP Chemistry. Welcome to Equilibrium. And by welcome to Equilibrium, what I really mean is welcome to the rest of our year. Basically, the rest of our curriculum is over Equilibrium. It's kind of exciting and scary at the same time to realize that we are getting pretty close to the end of our curriculum. Now, it's kind of interesting to say that the whole rest of our curriculum is over Equilibrium. Don't let that fool you. It's a really big chunk of Equilibrium. I think it's over 4 more chapters. We're going to work through Equilibrium, acids and bases. We're going to apply acids and bases, and then we're going to look at some additional acids and bases or equilibrium and how it relates back to solubility. And then we're going to revisit electrochemistry. But all of that can wait because we want to introduce you to equilibrium. So here we are. Let's get going. So before we talk anything about anything else, let's work through this concept of equilibrium one more time. So we have talked about this at various points of the year. Let's really hash it out right here. So when we talk about a reaction up until really this point in time, we have talked about the reaction as if it goes to completion, right? And we've done this this year. We did this last year in chemistry. You've probably done this in every class where you've ever dealt with a chemical reaction, right? We kind of treat it like we're baking cookies. We take a couple bowls of flour. I don't know, how many cookies are we making here? We take a couple cups of sugar. We take some pitchers of milk. Get a little handle going on there. That kind of looks like a pitcher of milk. We get a bunch of eggs. Of course, we have to get some bags, lots and lots and lots of bags of chocolate chips. That's totally what a chocolate chip looks like. I know you're all with me here, right? And in our typical goes to completion reaction, we mix all of this up and we get out cookies. Lots of cookies if we're using this many ingredients, right? We get out lots and lots of cookies. Okay, and in the end, what we pretend is that we don't have reactants anymore because they've all been turned into products. Well, this is not actually how most reactions proceed. Most reactions, the molecules start hitting each other, and if they hit each other with enough force and the right orientation, then they become products, right? And then the products start building up, and the products start involving themselves in these collisions. And if two products collide with enough energy and the right orientation, well, cookies start turning back into ingredients. The reaction can go both ways. In most reactions, especially the ones that happen in solution, aqueous solution, and especially the ones that we're going to talk about for this chapter and the next couple chapters, ingredients can turn into products and products can turn into ingredients. Reactants can collide with reactants and turn into products. Well, products can react with products and turn back into reactants. So usually what we're left with is not empty ingredients and lots and lots and lots of cookies, right? What we're usually left with is scenario B. We have some ingredients left and we have some products. And ingredients are being turned into products at the same time products are being turned back into ingredients, also known as reactants, right? This is equilibrium. And when those two rates are equal, when the reactants are turning into products at the same rate that products are being turned into reactants, that's our definition of equilibrium. It's not at completion. It's at equilibrium. We still have reactants left. We still have products left. The rates are going in both directions equally. So we have no net movement. We don't have a net gain of products. We don't have a net gain of reactants, but the reactions are still occurring. And so we call it dynamic. Maybe if I can spell dynamic. Come on, pen. Work with me. Dynamic. We call it dynamic. The reactions are still proceeding in both directions equally. It's dynamic. Change is still occurring, just not net change. It's more like cars going across a bridge, right? Cars are driving from city A to city B, but if the same amount of cars are going from city B to city A, if the cars are driving in both directions, then neither population is growing. It's dynamic. Cars are still moving, but neither one is gaining a population, so it's at equilibrium. Okay, now with this concept, we have a couple terms that just get thrown around. So rather than let you flounder in the terms, I want to define them so that you know what we're talking about going forward. First of all, we've already used two terms. We've used a term completion, and that's when we have no reactants left. We have all products. That would be completion. We just talked about the term equilibrium. So these are the two types of reactions that we're going to talk about. The other terms I want to talk about are far left and far right. So what these are referring to are the points in a reaction. If I say reactants are turning into products, right? Literally how I write it on the paper is I have a right side. Right side would be equivalent to products. And I have a left side of my paper, and my reactants are on the left. So if the reaction occurs and hits equilibrium, we need to be able to talk about how far it proceeds. Equilibrium doesn't mean I have equal amounts present. This term equal does mean something is equal, but it's not the amounts of reactants and products. What's equal? The rates, right? The rates of reaction forward and backward are equal. The amounts of reactant and product are not equal. So for example, let me draw this out for you. Let's pick a simple reaction. Na plus Cl minus goes to NaCl, okay? Na is going to be circles, Cl is going to be squares, NaCl is going to be a circle attached to a square. Got it? Okay, so let's say we start with 10 of our reactants. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we'll start with the same amount of chlorides. All right, and we're going to start with no products. So this is my initial amount. I'll write it over here as well. Initially, I have 10 and 10 and 0. Okay, now as these things combine and react, they are going to turn into products, right? So the reactants are no longer present because now they're present as products. Okay, so let's say one of each reactant reacts. Okay, so my change is -1. My products are +1 now, and that's where equilibrium occurs. So I have 9 of each reactant left. I have 1 of my product left. This would be a far left. We would say this equilibrium is far left. This equilibrium is far left. That would be the sentence that you see. And what it means is the reactions only occurred a little bit and before it hit equilibrium. So at this point in time, yes, reactants are still turning into products. Yes, products are still turning into reactants, but the rates of reaction are equal. I'm not getting a net gain or net loss on either side, right? So we've hit equilibrium. However, not many products have been made. The equilibrium is at far left. And by left, we mean on the reactant side. The equilibrium is slated towards the reactants. Now, let me give you a different scenario. All right, let's say most of these combine and form products. So I swear I chose the easiest shapes to make. Still, it's taking me a long time. They're starting to look more like little sheep. Started out as a circle square, turned into more of a bed. Now they're starting to look like little sheep by the end. Anyway, you get the idea. Okay, so these are no longer here. Come on, eraser. These reactants are no longer here. They have become products. And now I hit equilibrium. So let's say this is the point where I hit equilibrium. So if I compare it to what I had initially written, Na plus, Cl minus, goes to NaCl. Initially I had 10, 10, and 0, just like the first time. My change was what, 7? So I use 7 of my reactants. I form 7 of my products. I have 3 of each reactant left. I have 7 of my product left at equilibrium. Okay, this would be a scenario we would call far right. The equilibrium lies to the right. Now, the right side of my paper is the products. And so what that's saying is I have more products than I have reactants left. Okay, so if I'm at far right, my reaction has essentially gone to completion. Far right would be almost no reactants left, all products. This would be the cookie scenario, right? We want to use all our ingredients. We want to be left with no ingredients. We want to have all cookies. That would be a far right equilibrium. Our cookies are not turning back into reactants very early. It waits until the reaction has proceeded to inform lots and lots and lots of products for that to happen. You can see a couple examples down below. Look at our far left example. Calcium oxide turns into calcium metal and oxygen gas. Now, this may happen if you have calcium oxide. Some of it may decompose into calcium metal and oxygen gas, but it's not going to happen very much, right? Calcium metal is extremely reactive, especially with steam, I believe. Calcium oxide is a pretty stable compound, so not much of our reactant is actually going to decompose into products. We're going to be left with mostly reactants and maybe a little bit of products. Whereas hydrogen gas and oxygen gas reacting to form water, if we get over that activation energy hump and have our initial spark, right, this reaction is really going to roll until we have very little gas left and we have all water present. Our equilibrium will go to the far right. But again, most things stop before actually hitting completion. Most reactions go to an equilibrium, not a completion. Mathematically, it's just harder to deal with. Think of stoichiometry, right? We spent all this time in chemistry working through stoichiometry. Well, we didn't want to stop halfway and explain, oh, actually, they don't all react. Let's deal with fractions here, right? We didn't want to do that to poor, sweet, innocent, starry-eyed chemistry students. We're not going to do that to you until you are you guys, AP chemistry students who are no longer starry-eyed and you know the realities of chemistry. You're ready. You're ready for this. Let's do this, shall we? Let's figure out where reactions actually stop and not this hunky-dory Disney family of a completed reaction, right? Okay, so here's the deal. When we go towards equilibrium, we have this stopping point. And the stopping point depends on this balance between reactants and products, right? This is what we keep coming down to in all of these scenarios that we have written on the board right now. If we look at equilibrium, look at how we've described it. We've described it as a comparison between reactants and products, right? And that's exactly the concept we need to introduce in order to keep talking about equilibrium. That's exactly what we avoided introducing in chemistry. What you guys are so ready for now is this relationship between reactants and products. And this relationship is something that we call K. We need this relationship to be relayed to us. And basically, we do it in the form of a ratio. So we're going to do it in the form of a ratio between products and reactants. Now we're going to get farther into this, but while we have these examples on the board, let's tie it to this. Okay, so we're going to talk about where equilibrium occurs. Yes, this ties back into stoichiometry. Okay, but we need to talk about where equilibrium occurs, and really it's this relationship or this ratio between products and reactants, and it's called K. K is the law of mass action. And roughly, K is a ratio between products and reactants. So when we say far right or far left, these come with numbers. Now, K is a little bit more complicated than this, but before we get into what K actually is, let me show you how this plays out. Let's just take it as if it's a true ratio, true simple ratio between reactants and products, right? So let's go reactants on this first one versus products. So products are going to go on the top, 1/9. Okay, 1/9. Now, this was a reaction that had lots and lots of reactants present. So our denominator is going to be big. Not very many products present. Our numerator is going to be small. And look what our fraction comes out to be. If a ratio between products and reactants are looked at, that ratio is going to be a pretty small number. What, 0.167 or something like that, right? It's pretty small. Actually, let me give you a real number so I don't have to confuse you with my approximations. Okay, 0.11. There we go. It's a pretty small number compared to what this fraction would be, what this ratio would be if we were far right, if we had lots of products versus very little reactants. So in that case, it would be 7/3, right? Which would be over 2. What is it? 2.3? Yeah. 2.3. So when we are far left, when our equilibrium it lies to the left, our ratio tends to be small. Products over reactants tends to be a fairly small number. If our equilibrium lies to the right, our ratio gets bigger. The more products that gets made, the more our ratio gets bigger. And this is what we're going to see. We're going to use this K to communicate where our equilibrium lies. The smaller K is, the less the reaction happens. The bigger K is, the more reaction happens. The smaller K is, the less products are formed. The bigger K is, the more products are formed. So these are the ideas that are coming together in this chapter. Okay, so I want to give you a little bit more example, talk a little bit through this concept of equilibrium, and then introduce you to the real K, the real law of mass action. So let's keep going here. Okay, so all of this comes together to describe a couple things. So this is kind of where these are the concepts we want to come out with this chapter with. How and why a chemical system comes to equilibrium. So how a chemical system comes to equilibrium and why it actually goes to equilibrium. What equilibrium looks like, what kind of characteristics are present when we hit equilibrium, and then how can we actually calculate concentrations of reactants and products. We know how to calculate concentrations of reactants and products when our reaction goes to equilibrium or goes to completion, right? We did this in chemistry in our stoichiometry unit. But how can we do this if when it stops halfway? How can we calculate those concentrations? Okay, so that's kind of what we're going to come out of this chapter with. So here you can see it graphically. First of all, we are talking about dynamic equilibrium, right? So we want to show symbolically in the reaction that these rates are still progressing forward and backward. So you're going to see arrows that kind of look like this, right? Before we just said like A goes to B, right? And we assumed it was completion. Well, now we're dealing with equilibrium. We want arrows in both directions. And so the arrows that you see tend to be half arrows because we are efficient scientists, right? Now, half arrows like this symbol is kind of hard to find on all the various programs that we use. And so I tend to end up typing something that looks like this. So just know those mean the same thing. They both mean the reaction rates are happening in equal directions. Okay, you can see down here, we can communicate these graphically. So again, like everything else in the world of science, it comes down to relationships, right? And here we have a relationship of concentration versus time. This should look very familiar, right? This would be an integrated rate law if we're talking about the relationship between concentration and time. Oh, rate law. Okay, but you can see here that in the beginning, when we had products, when we had all reactants and no products, right? 1 something, let's pretend that's moles of A and 0 moles of B, that our reaction is just going to proceed forward. We have no B. There can be no reverse reaction, right? As the reaction proceeds, we get less and less A. So our forward reaction is going to start high and then decrease a little bit, right? We saw this with like the method of initial rates, or looking at concentration versus time data and trying to figure out the order of rates. We saw that the rate changes or concentration changes as the reaction proceeds. Now, in a similar way, as B accumulates, the reverse reaction is going to start to grow. So notice here we have a relationship where the forward reaction is still stronger, is still more dominant, but there is a reverse reaction starting. And then eventually, notice we hit these concentrations of B and A that kind of flatline, right? B is no longer changing. Neither is A. Remember, it's still dynamic. So B is forming A and A is forming B, but at the same rate. And so there's no net change. There's no overall change. And then look at the reaction rates. You can see those arrows are now equal, trying to indicate that the forward rate and the reverse rate is backward. So this is what equilibrium would look like on a graph. You should be able to look at a graph and tell me exactly where the point of equilibrium happens. We can do it for this second graph. Look at this graph and tell me where equilibrium happens. I would say here, 60 seconds is about where equilibrium happens, because about at 60 seconds, the amount of B and A stop changing, right? They're changing up until that point. Now, there is a difference here. First of all, a couple differences. This might actually be a good place. This would be good practice for you if you pause the video here and looked at differences between these two graphs. Name as many differences as you possibly can say. All right, difference number one. Notice we start with B, all B and no A. We're starting with the reverse reaction, right? So notice here we have all reverse reaction and no forward reaction. It builds up. It builds up until they're equal. Second of all, notice that the amount of B and amount of A we end with are still the same. So no matter what we start with, whether we start with all A and eventually form B, or we start with all B and eventually form A, if we change nothing else about the reaction, right? We don't change the temperature, we don't change the pressure, we just change the concentration of our initial amounts. Notice the exact same amount of B and A is going to form. And this gets us back to thinking about K. K is the ratio of products to reactants that happens at equilibrium. This ratio is always going to be the same. Now, we may end up with, if we mess with the initial concentrations, let's say K, let me do this in a different color. Let's say K is equal to 2, okay? Well, if we change initial concentrations, we might have 4 products and 2 reactants present at equilibrium. And that gets us to a ratio of 2 or 2 to 1, right? Or we could hit that at 0.5 reactants and 0.25, 0.5 products and 0.25 reactants. That still gets us to a K of 2 or a ratio of 2 or a ratio of 2 to 1, right? So if you mess with initial amounts in your reaction, you may end up with different amounts of products, but the ratio of products to reactants at equilibrium will always be consistent. K, the law of mass action, capital K, this ratio of products to reactants will always be the same. The ratio will be the same, not the amounts of products and reactants, right? Those can be influenced, but the ratio will always be the same until you change the conditions, and then you can screw up your ratio, right? Always. Okay, so this is what the law of mass action is. All right, so this idea of equilibrium gets us into thinking about how we can manipulate reactions. Okay, so if we're at equilibrium, concentration of reactants and products remain constant because forward and reverse reaction rates are equal. That's the definition of equilibrium, right? What if then we inject water into this system? So here's our reaction that's happening in our system. Our system comes to equilibrium, check. Once we're at equilibrium, we inject water into this. Let's think on a molecular level of what happens. So we increase water. That means we have lots of water molecules, more water molecules than we had at equilibrium. And those water molecules are going to collide with carbon monoxide. The forward rate is going to speed up. We have more molecules, we're going to have more collisions, we're going to have more forward, a forward reaction rate. As reactants form products, our products are going to build up, then the reverse rate is going to speed up as well, and a new equilibrium is going to be established. A new equilibrium, which has new amounts of all our reactants and products, but our ratio between them is still the same. When equilibrium happens, it always happens to satisfy this ratio, even if the amounts have to shift and change. Okay, so there's a couple factors that affect this equilibrium position. So when we say equilibrium positions, what that means, it's the concentrations of the reactants and the concentrations of the products. So this is kind of what we were getting to before. Let's say we go back to this simplified reaction of A goes to B, right? We could have in our K, our law of mass action is going to be equal to 2. So we could have a scenario where we have equilibrium positions of 4 moles of B or 4 molar B to 2 moles of A. This would satisfy our ratio. Or we could have different equilibrium positions of 0.5 B, 0.25 A, which would still satisfy our law of mass action of 2. Notice I have 2 different sets of equilibrium positions. Equilibrium positions is referring to the concentrations of reactants and concentrations of products. The law of mass action is different. The law of mass action does not change. The ratio between the equilibrium positions does not change. The equilibrium positions themselves can change. They can change so that they always satisfy the law of mass action. They always come to the same ratio. So what can affect equilibrium positions? What can affect the concentration of reactants and products at equilibrium? A couple things. First of all, initial concentrations can, just like that other slide we were just on. If you're at equilibrium and you put more reactants in there, you're going to shift all the equilibrium positions to minimize that stressor, to absorb the extra molecules that you just put in there. The equilibrium positions are going to shift so that they still satisfy the law of mass action. What else can shift these equilibrium positions? Well, relative energies of reactants and products. The energies of the reactants and products. When we're talking about that, we're talking about an energy diagram. Where are the reactants? And relative to the reactants, where are the products? This can affect the equilibrium positions of reactants and products. This is why not all reactions have the same ratio. All reactions have their own individual ratio of products to reactants. A to B might have a ratio of 2. C to D might have a ratio of 1.2 times 10 to the negative 8th. Okay, those relative energies of reactants and products are going to lead to different equilibrium positions, but the reaction has a very consistent law of mass action. Okay, in a similar way, relative degree of organization of reactants and products can also affect these equilibrium positions. When you see this word organization, a red flag should go off in your head. What are we talking about when we're talking about organization? Entropy. So equilibrium is related to thermodynamics. Yes, it's all related, right? And we'll get to, at the end of this chapter, we're going to circle back around and talk about how equilibrium is related to these thermodynamic quantities. Okay, if you're observing a reaction and no reaction appears to occur, there are a couple different possibilities. First of all, your system could be at equilibrium. No forward, no reverse reaction appearing. There's no net gain in any direction. You could be at equilibrium. That is one possibility. The other possibility is that it's not necessarily the equilibrium that it's at, but it's that your rate is very slow. If the reaction is so slow that the rate can't be detected, you may not be at equilibrium. Leave the system for a couple thousand years, come back to it, and you may find different equilibrium positions, different amounts of reactant and product because you weren't actually at equilibrium 1,000 years ago. Silly you. So it could be, if you see a reaction and it's not actually moving, it doesn't appear to be moving, it could be the rate of it is too slow, but you're not actually at equilibrium yet. Okay, so you kind of have to be careful with that when you're working with reactions in the lab. And here we go. So this is the real K. This is the real law of mass action. So this ratio that the equilibrium positions always satisfy can be found from the reaction. You can take a reaction and you can build your K. Notice that we have products on the top, and those products are in terms of concentration, not moles, not mass, not volume, concentration. Also, notice that the concentrations are raised to the coefficients. And then on the bottom, we have the same thing for reactants. So basically, it is a ratio between products and reactants, but it's a very specific, mathematically specific ratio. You have to get it right. These are reflecting concentrations of each of the chemical systems at equilibrium. If your ratio matches K, you are at equilibrium. Notice it's dependent on coefficients, and then K is the equilibrium constant or the law of mass action. So we can look at a reaction and build this K. We'll do this here, and then we'll come back together and practice it. So we want to write the equilibrium expression or the equilibrium constant for the following reaction. This would be a good place to pause your video and try it, and then come back and see how you do. Okay, notice on the top of my denominator, or my numerator, the top of my fraction, which is called the numerator, I have my products. I have them in brackets indicating I'm going to use concentration, and I have those brackets raised to my coefficients. On the bottom, I do something similar, concentration of ammonia to the 4th times concentration of oxygen to the 7th. Okay, so this would be my equilibrium expression, my equilibrium constant, my law of mass action for this specific reaction. And K is going to have a specific number, a constant, as long as your temperature is also constant. Change the temperature, you get a different K number for K. Keep the temperature constant, you can manipulate all sorts of other things, pressure, concentration, volume, size of container, all kinds of things. And even like catalyst, surface area, and you will still come out to have equilibrium positions that satisfy your equilibrium expression. Okay, so think about this for a little bit. We'll come back together. We'll practice this. Welcome to the world of equilibrium.